Okay, so this is day 2 of Unit 2. Normally today you would have had your test, and there are 2 reasons why you're not going to have your test today. One, my fault, I dropped the ball with second period. I already have apologized to them on that with the last day of notes on Unit 1. Now get this, I recorded it for you guys, and that was awesome. But when I went to YouTube to play that video, audio didn't record because this did not record audio, but it is now recording audio. So it was just a big video of silence. So what I'm going to do is I'm going to go home. If not this tomorrow, I will do it tonight by staying here on a Friday night, but making sure that you guys are well prepared for the Tuesday's test by actually playing it on my laptop. And I will have a small little video of my face at the very bottom right commentating on my own video that I recorded from before, so you can hear my audio overhaul, whatever, on top of the, so you can hear my audio track on top of the video.
And we get to see your face.
And you get to see my face. So I would try to make it as entertaining as possible. Okay.
Like puppets.
The second reason why I did it was because College Board has this new awesome thing to where it's an online resource that gives you guys a lot of practice for the actual AP exam. So across the nation, across the world, everyone who takes the AP exam, before they were a little bit at like a crapshoot of, am I going to get good questions in preparation for this test? And it all depended upon what their teacher has, okay? We have really good resources. We've always had really good resources, but here's the thing, some schools don't. So kind of balancing the playing field, that's why they did that, which makes our job even higher to where we got to rise above the challenge and continue to push, because these scores are always based on how did everyone do. You see what I'm saying? So you are always compared to everyone and seeing, okay, here's the mean, here's the average, you all got 2s and 1s, you all got 3s, 4s, and 5s. You see what I'm saying? And then they go from that in a lot of respect. With that being said, there are unit checkpoints. Basically, for each unit, I can assign you problems, multiple choice and free response questions, to where you'll see it and you'll be like, you'll be so well versed with these questions that when you get to the AP exam, it's just another, you know what I mean? Another unit, whatever, questions. And here's the thing, that data is for us. That data is for me to see what do they struggle with? What were they really strong with? So then I can start building more questions as we get closer and closer to the AP exam, and even just spiral throughout the entire year. I need to strengthen them with this. I need to strengthen them with that. You see what I'm saying? But then it also communicates to the administration, you know, how are we doing as individual classes? How are we doing as far as, when we have 5 or 6 high schools here? You see what I'm saying? Just to make sure everyone's accountable. And at the same time, I think it's for College Board to see what are kind of questions that they struggle with. And if they struggle with these types of questions, we're going to give more of those on the AP exam. You see where I'm going with this? So it's also to see where you're at as far as concept and topic type questions. So I will record a video today that shows you instructions. One of my students, Luke from second period, is already on. He helped me out this morning to make sure that you guys were able to get on. That will show you instructions on how you can get onto your account and what it's going to look like. It is required, but it is not for a grade. Okay? So instead of giving you a bombardment of supplemental homework, these questions are supplemental homework type of questions. But the good thing is that it will tell you as you go through if you got it right or wrong and what you were struggling with as you go through. Does that make sense? To me, I think it's phenomenal because it gives you a glimpse, basically, of what the test is going to be like, because we get our tests from that bank of questions from College Board. So they have just a bank of questions that we could just do IBT, and it just lists a bunch of questions that are IBT, and we can just pick whatever ones we want. And that's how you're tested. So in a sense, you're getting the test if you do it to the level that we're wanting you to do it before doing the test, aka test review. Go with me? Okay, so it is, again, it's not for a grade. It never will be for a grade. think you should do it. I think, and I'm not going to say it's mandatory, and if you don't, I'm going to take off points. No, but I think you should do it for sure. Okay? Questions? Okay, so second period, I recorded some continuity problems. And in your period, I'm going to record, bless you, some IVT problems. So that you will have supplemental homework, College Board test review online resource. You'll have videos of continuity. You'll have videos of IVT. You'll have a video with me, with my voiceover, and all is good, and we're back on track. Okay? Yes?
Should we, to study for the test on Tuesday, should we only do the college?
That's a good question. That's a good question to me. That's a good question. Should we just do the College Board? I'm going to say it depends on what grade you want. If you want to make sure, like your average is at least 98 or 95 right now, and you want to keep it there, I would say do what you need to do to make sure that you feel comfortable with the information. Okay? And as far as that whole, and that might be College Board and supplemental, or that might be, I just went and saw a couple videos just to refresh. Whatever it is for you, okay? What was I saying? I was about to say something over just now.
Oh, you're recording the IVT problems.
No, not that. Forgot it. No worries.
All of our resources, the videos.
Oh, I was talking about Flipgrid. Flipgrid is going to be after the test. I just wanted to reiterate that. Okay? So the intro to this video, which is probably already 10 minutes, is just going to be on the screen, but I need to communicate all that to you guys. So that's good stuff. All right, so now let's go ahead and begin. Okay, we looked at definition of the derivative last time. And just a reiteration, this was a very cool function that would give you an equation in terms of x that all you had to do was give it a value and it will give you a velocity. It will give you the rate of change known as f prime of x. You with me? So let's say that it said f prime of x is equal to 4x squared. Okay? And let's say x represents time. And I put at 2 seconds. Okay, so at 2 seconds I would put a 2 right here. And I would say that the rate of change on f at 2 is going to be what? Anyway, 16. You with me? So this tells me a velocity. And usually velocity is like meters per second, feet per second, miles per hour. Units of measure. Okay? So let's say this is feet per second. Make sure that we understand from last time that f prime of 2 is different than f of 2. Okay, f of 2 is going to give us a position where f prime of 2 gives us the velocity at said position. Okay? I believe we were talking about this last time. We talked about inception, right? Okay, so inception, f of x, I'm just going to do an easy problem. Don't worry if you can't see the math yet, but you will by the end of today for sure. Let's say f of x is 3x squared. And then f prime of x is 6x. And then f double prime of x is 6. Okay? Now, to get from here to 6x, we would do this definition of the derivative right here. And just real quick, we would build our f of x function by saying 3 times x plus h squared. What we just did was y2. F of x plus h. And then we're going to subtract f of x, which in this case is 3x squared. And it's all over h as h approached 0. And this is our derivative function, f prime of x. We simplify this, we get x squared plus 2xh plus h squared, all multiplied with the 3. And then the rest. Distribute this, we'd get 6x squared plus 3x squared plus 6xh plus 3h squared minus 3x squared all over h as h is approaching 0. You see, anything without an h will cancel to what? 0. Nice, because you're adding in the numerator or subtracting. So everything that has an h left over will reduce because you're GCFing at that h, and you reduce it to something that looks like this. So you just canceled the piece that otherwise would have made it undefined. So you're now going to plug in for h. And that's why f prime of x, in this case, is equal to 6x, aka the velocity function. So this one tells you position, this one tells you velocity, and if we did the same thing, all we did is we found all the slopes that could exist on all real numbers of this original graph with this function right here. And slopes, aka derivative, is the same as what we used to call m, we're now calling f prime. You with me?
So just to make sure, f of 2 is like a point on a graph, and then f prime of 2 is like the slope?
Okay, yeah, the slope. And then, so we're going to change the word slope to something a little bit more understandable to the level that we're doing it now.
Right.
No worries. Yeah, but we're going to get there real quick. But I still like the word slope in the respect of, guys, what's the slope of this constant linear line? 6. Is it always 6? Yes, it's always 6 on this one because y equals, or a function that's 6x has a constant slope. You with me? So this will always be 6. Now let me break it down to you in real world application. If it's real world application, just like Danielle was saying, the first one gives me the position. So what if I said, what is the position at 2 seconds? Well, the position would be what? 12. What would the position, or sorry, the derivative, aka the velocity, be at that 2 seconds? 12. And what would be the acceleration of that particle in space, if you will, at 2 seconds? 6. So imagine that you have a particle that you threw up. Okay, so you're holding something right here, and you throw a rock upward. And while it's upward, you took a picture while it was in the air. A picture is worth 1,000 words for sure now, because this will tell you at 2 seconds, it was 12 feet high from the ground. And at that same moment in time, 2 seconds later, right, at that same 2 seconds, how fast is it moving upward? 12, in this case, let's say feet per second. And last but not least, this last particle here, or this last equation will tell you it's accelerating at 6 feet per second squared. Now, I don't need you to master the acceleration and velocity quite yet. I just want you to understand why we even have derivatives. The derivatives is so we can project and predict the future. Remember in Algebra 2 we used to use these things called lines of best fit? It almost predicted the future. This has very, very little error to where it is so exact and precise, it's pretty scary of how it actually works. Okay? Alright, so this f prime of x, definition of the derivative, will find an equation that can give you all slopes or m's, or rate of changes, with an equation. The alternative form, which we still need to learn, gives you only one slope. So remember on those equations over here that I had 6x was f prime of x? Guys, I could put 2 in here, it's 12. I could put 3, it's 18. You with me? I could put -1, it's -6. I could put all kinds of values and get an answer. But with the alternative form, it's only when I'm trying to find one derivative. One specific derivative located at C. Does that make sense? So here we go. Let me give you an example. Let's go to this equation here. We did this last time. And when we did this, the derivative function that we got was 2x minus 4.
Do we have to learn both forms?
Yes, we have to learn both forms. Because on the test for Unit 2, I will say using the alternative form, show your work and give me the derivative at this point. And you have to show all the work.
What about the difference?
And the definition too. I'll say using the definition of the derivative. But if I don't mention which one you have to use, which one do you think I think you should use?
Definition.
The definition of the derivative.
But there might be questions where you say you have to use the alternative.
Yeah, for sure. Here we go. So now, f prime of 3 with what we saw for last time, anyone, would be what? 2. Because 6 minus 4 is 2. And if I wanted to find the derivative with the alternative form, I would have to know how to set it up first. It would be f prime of what? Of 3. F prime of 3. Okay? The derivative on f at 3 is equal to the limit as x approaches 3 of f of x minus f of 3 over x minus 3. This right here is just one slide back that I was showing you. Remember those two equations? One was definition, one was the alternative form.
What's the alternative form look like without anything plugged in? Like what are
So the alternative without anything plugged in is f of x minus f of c over x minus c as x approaches c. Notice that it's very similar, and thank you for asking, Braden, because I want to show you right here. It's very similar to the definition in the fact that the denominators are both approaching what? 0. They're both approaching 0. You with me? One just makes it look a little bit more difficult, but it's not bad. Let's look at the similarities. They both have f of x. It's just different of where it's located. So if I wanted to set this up right here of f of x, I'm going to go to my equation, which is f of x, and I'm going to write that right here. Okay? And f of 3, because c is my constant, and it is right here at 3, bless you, f of 3 means what is the y value, or what is the output answer on f if I put 3 into the original position function. Okay? What would I get? Negative 3? So I have f of x minus f of 3, which is negative 3, all over x minus 3. If I simplify the top, a negative times a negative becomes a positive. So I'd have something that looks like that. Oops. Come on. And what do you think I'm going to do next? I'm going to factor the top to what? X minus 1, x minus 3. So now, guys, notation, especially since I'm giving you a little bit extra time, notation is big with your first unit test, the test that you're going to have on Tuesday. Please make sure all the limits that you are showing that limit until you finally plug it in, just like you did on last time. But I'm going to grade it more difficultly, okay? I'm going to, with a fine-tooth comb. These will cancel. And this is the one that I'm looking for. I'm looking for that. Because then what will my answer be, guys? 2. My answer is, look at this. F prime at 3 is 2. Same answer, just a different way to get it. But get this, I can only use this equation to evaluate what specific x value?
3.
Just 3. I can't find what is f prime of 8 unless I do the entire thing all over again. You with me? But with the definition and derivative, I don't. Okay? So here we go. My slope is 2. And I have a point that I'm going to use both bits of information to answer this piece right here. The equation of the tangent line. You know this, and a lot of you might have been reluctant to use it in Algebra 1 and Algebra 2 because you liked the y-intercept much better. But I'm telling you guys, this one is what we will use most of, and it's more efficient. Okay? So, the slope. We have the slope is 2. Can someone tell me what is this x value going to be from our problem?
3.
3. We're looking at this moment in time when x is 3. So this will be 3. And can someone tell me, what do you think I would put here for y1? -3. Because f of 3 is -3. 9 minus 12. So I know that you're used to way back when of seeing point slope formula as 3, -3, and the slope of seeing it as 2. And from here, it's just the same. Only with calculus, we say it's f prime of 3 is equal to 2. And we say f of 3 is equal to -3. You should now be able to see this and this the way you used to see it in Algebra 1 and 2. So now let's build it. Y minus y1, which is subtracting the negative, is the same as adding, times or equals m times x minus x1. This right here is the equation of the tangent line. Okay? And you're used to seeing this differently. You're used to seeing it as 2x minus 6 and then moving it over to get this. Go with me? So now if I go to this original thing right here, and we talked about this last time in last videos, and I were to graph it real quick, x minus 4, we have zeros at x equals 0, and we have zeros at x is equal to 4. It's positive, so it goes up, and it looks something like this. Remember this? Now, this tangent line says that it will touch this graph at one point. That's what tangent means. Touching it at one point, just like we did in geometry. This line is tangent to this circle. Does anyone remember what angle that this touches this circle at? 90 degrees. So tangent, in this respect, is touching it at 90 degrees. Okay? So 2x minus 9 will be the equation of the line that touches at x is equal to 3. So 1, 2, 3. Right here is where I'm going to draw this line. And when I draw it tangent, check this out. The y-intercept will end up becoming 9, or -9. And the slope, aka rise over run, of this line is 2.
How did
of the entire thing?
Of the tangent line.
Remember we did the definition of the derivative and we got 2?
Yeah.
And we also did the alternative form and we got 2. So all that work that we did was to find, this is a big question, the steepness of this line. Go with me? Because if I have, here we go, say I have this line here. Here we go. I like his timing of the question too, for sure. Am I on it? Am I on it? Oh, that's pretty good. Pretty close. So that is my slope there. Now, if I were to move throughout this equation, this could be the slope right there. You'll see how I'm doing this? It's where the graph will touch the original position function basically at one point. This could be the tangent slope at x is equal to 0. Do you see how I'm doing this? And then let's say that I wanted to choose x is equal to 1. So I would make the slope touch the graph right at x is equal to 1.
So we just, if we wanted to know what that is, we plug -1 into f prime.
Yep. And the steepness of this slope in real world application will tell you the rate of change of it, like the velocity, if you will. So look at this. This is like a -1. So that means something's going backwards or to the left. You know what I mean? In that negative velocity respect. We're jumping big time ahead, but you're asking the questions. That's why I'm going with it. If you don't understand what I'm doing as far as the connection with physics, no worries. You don't have to understand it yet. Okay. Like you don't even have to understand it for another 2 units. Alright, so now let's do a quick sketch of what derivatives are looking like. Just a quick one. So at 0, what's the position? 0. At 1, what's the position? 1. And then 2 is 4. And -1 is 1. And -2 is 4. But if I ask you, what is the derivative at 0, 0, I'm asking you to draw me a tangent line. And what is the slope, otherwise the velocity, rate of change, at x is equal to 0? 0. Now this might feel a little bit uncomfortable, but now I need a volunteer to come up and draw a slope at 1. So at x is equal to 1, Alec is coming up and he's going to draw what he thinks a tangent line would look like touching the graph at x is equal to 1. Yep. So here's the thing. Thank you. The tangent will touch at how many points? 1. For sure it will touch at 1 point. And his points... No, it's okay. I know what you were doing, and it's still correct. But here's what I want you to make sure that you do. When you're looking at a graph, and if you're trying to draw a tangent, let's say right here, this is not a good tangent. That one would not be a good tangent. This one would not be a good tangent. Do you see where I'm going with this? What a good tangent would be when there's the same amount of room, basically, in between those pieces. It almost feels balanced, like a seesaw, if you will. Are we good? Okay. So, what do y'all say f prime would be at 1? If you were to approximate it and just guess. Well, you could go to a corner to a corner. You'll see where I'm going with this? And what's the rise over run? Up 3 over 2. So what do you think it would be here at -1? It would be down 3. over 2. All we're doing is drawing tangent lines. Now, a good approximation here, I need a volunteer who could draw me a tangent line at x is equal to 2. So at x is equal to 2, Alec is getting 100 points for his team. Volunteers would have gotten more points. But here's the, Omar, come on up. So after my explanation, Omar's team will get 25. But Omar's going to show us a tangent at x is equal to 2. Go for it. Okay? So that's a pretty good tangent. It is equidistant from the left as far as the same spacing here and the same spacing here. It's pretty balanced. Would you agree? Okay. So let's look at this and let's calculate a rise over run approximation. What does that look like to you? It looks like this could be where a corner would be, right? This is where a corner is. So it almost looks like 1, 2, 3, 4, 5, up 5 over 2. Okay, so over here at x is equal to 2 is up 5 over 2. And yes, this negative 3, my apologies, I'm just now seeing this, belongs with the negative 1. All we're doing is looking at the steepness of a line.
So, those approximated.
Oh yeah, these are big time approximations.
Oh, okay.
No, you should.
I was
And
wondering. I
a
thought
lot of
it was like
people freak
exact
out
values.
because they're trying to see exact and they're trying to calculate it. The only way you can do exact is to do what? To do the math, to do the algebra, to do that long way of definition of derivatives or alternative form.
Do the power of
Oh yeah, yeah, that's coming.
2x.
Oh, thanks for saying that. Good timing. Don't do power roll on the test for Unit 2 or you will not get credit for that. Okay? You have to know how to show the work and do the work. All right. Yes.
Is there any time where you like have to use alternative or have to use definition, or can you use
You can use either one and they both will work.
for like any problem?
So here's, and I love the question. Here's what I'll say. Which one did you have to use when you were using stuff back in Algebra 2? Did you have to use slope intercept and y-intercept? Or could you also have used point slope formula? You could use either one. Which one was more difficult for people to use? Was point slope. They didn't see it as easily with point slope. But either way, it will work. To me, point slope is to alternative form as y-intercept is to definition of the derivative.
Wait, so doesn't the definition one give more information?
It does.
Yeah.
It does. It gives you so much more information. So by default, my hope is that you use that one. Okay? All right. So now we're going to talk about differentiability. So differentiability is basically its ability to be differentiated. Where can I actually find a derivative? Okay? And it ties in a lot where you're going to be tested on Tuesday. And it's just extra foundational support. A function is not differentiable. That means I can't find a derivative the way we did graphically if the followings exist. If there's a cusp, I cannot find there to be a slope right there. I can't. Even though it's equidistant, I can't. And the biggest reason why, it's a sharp turn. I can if it's a slow changing and say, I want to find a derivative here. Well, yeah, the derivative is that. But if it's all of a sudden drastically changed, you can't use a derivative, or you can't find a derivative because it was a drastic change. Imagine this. I want you to imagine that this graph right here that we're looking at, this drastic change, let's say that you invest. And your investments are going down. And you can see the trend. They're going down at down 2 over 2. They're going down at a slope of -1. let's say you couldn't look into the future. Like right here to the right, you had no idea what the graph was about to do. If it was slow changing, like a curve, you could predict what it was going to do. It's called local linearity. Okay? You could predict the future. But if it's a drastic change, a sharp turn, a drastic change, could you have predicted that? No, there's no way that you could have. So derivatives are predicting the future. They're trying to find the rates of change by trying to project the future before it happens. But it can't be a drastic change because no one could predict that. You with me? Alright, here's another place where you cannot take a derivative. You can't take a derivative where something doesn't exist. So if there's a hole in the graph, I cannot take the derivative at that hole. You with me? So if I'm looking at, let's say that this is x equals 3, I could not take the derivative because it doesn't exist. Rule 1 of continuity says that something has to exist first as a point before it's even continuous. That's the same thing kind of going on right here. So this vertical asymptote, you could not be able to predict. You can't take the derivative there. Okay? Let's move on to, this is another time that you cannot predict the future, aka find a slope. Because what is the slope, if I drew it, of that tangent line? Undefined. You're dividing by 0. Let's say that I'm looking at this with 2 points. Let's say 0, -1, and 0, 1. If I did this like y2 minus y1 over x2 minus x1, I can't divide by 0. It's undefined. And this is an undefined slope. And we know that from tangents like in pre-calc, straight up and down. And then a cusp can also look like this. It doesn't have to be 2 straight lines. Any time that it comes to a drastic sharp turn change, we're going to call this a cusp. Because you can't predict, because it's not slow changing, it's not a smooth curve with local linearity.
What's the difference between the fourth one and the first one?
There's no difference. It's still the same thing. You know what I mean? A cusp is a cusp.
Yeah.
It's just the way it looks. It could be a little bit different sometimes. Now, let's move on to B right here. We're going to use the alternative form to find the derivative at C. In other words, we're trying to find this. We're trying to find 2. The derivative at 2. Okay, how do we set this up?
X minus 2 power 2/3 minus
Put up just a bit. Limit of, go ahead,
X
X approaches 2 of what?
x minus 2
F of x, yep. X minus 2 to the 2/3 minus
0. No.
f of 2, right?
Yeah, sorry.
Okay, no worries. Over x minus 2. You're right, it is 0, but I want people to know where that 0 came from. Guys, please, please, please write this in your notes. I want all numbers that are fractions to have horizontal lines. Please do not write 2/3 like this ever. Don't. Because if it's this that you're trying to show me, and you wrote it like this, you're wrong. Because this is actually that. You see what I'm saying? So I don't want people to show me diagonal things with numbers because sometimes we don't know what that really means. If I wanted to show this and you showed it with the diagonal, you would need parentheses there. You'll see where I'm going with this? So please, numbers forevermore, I want you to write them horizontal. The only thing that I want you to write that are diagonals are units of measure. Like feet per second, accelerations, velocities, stuff like that. Okay, f of 2. That means take this 2, plug it into f, and tell me what I get. What would I get? 0. So this is basically that. Now, what we have to do is find a way, if we can, to get rid of this denominator. Can we find a way to cancel x minus 2 from the denominator? Let's go back to algebra 2. If I have something with the same base, what do I do with these powers? I subtract, right? I subtract. So it'll be 1 is on the bottom, 2/3 is up top, aka 3/3 is on the bottom, 2/3 is up top. Who wins? The bottom by how much? 1/3. So you could write it simplified like that. Or you could write it simplified like this. My question is, someone asked this from before, will I always be able to cancel out that denominator piece? No, I will not. This one I can't cancel out. So what is my answer going to be anyway? Undefined, in this case, does not exist, right? Because it's a limit. Are we good? So this does not exist. We just found that the derivative does not exist at 2. Okay? Alright. So now, let's move on to this piecewise function. And I want to find, when c is 1, what's the alternative form? And I want to find f prime at c. Otherwise, f prime at 1. So the alternative form, here we go. The limit as x approaches 1. We know the bottom is going to be x minus what? 1. There's my, it's going to be dividing by 0 moment. And it's f of x minus f of c. So it's f of x minus f of 1. Guys, what f of x do I put here?
3x.
3x, yeah, because it's equal to. What's f of 1? 3. What should I do? GCF. And what would it would cancel out to the most simplified form, and you tell me, what would I get from my answer? I'd get 3. So f prime at 1 would be 3. However, let's come back and let's look at this piecewise function the way we used to in algebra 2 in pre-cal. And I'm going to draw 3x, which is this graph right here, but I'm only drawing it where it's bigger than or equal to x is equal to 1. So it would probably start here and go up. And here's 1. Go with me? And then I come over here and I get this piece. I'm going to look at what if moments. What if x equaled 1? Well, on this graph, I'd have 1, 3, which is what I just drew right here. And on this graph, what would I have? 1 what? 1, 3. So I'm going to go from a graph that looks like a quadratic that has been shifted up 2 units so it's going to be right here. A quadratic that would normally be written like this, I'm only going to draw it where it's less than 1. So it would look like that. It's open on the blue, but it's closed on the red. Is this continuous at 1? Yeah, it's continuous at 1. And if I were to find what is the derivative, do you think I would get a derivative of 3 on this other equation as well? Let's find out. Okay? So the answer is no, but let's make sure we know why. This almost feels like the second rule of continuity, where you have to test both one-sided limits. One approaching from the left and one approaching from the right. Okay? So what we're going to do now is we're going to do what is f prime at 1. It's almost like a what-if moment with derivatives of the first equation. So the limit as x approaches 1, where we're going to do it of f of x minus f of 1, which in this case, what did we say f of 1 was, guys? 3. Over x minus 1. We're still doing the alternative form, but we're doing it with the other equation, almost like evaluating both one-sided limits.
Shouldn't you write limit as x approaches 1 from the left?
You don't have to, but you can if you want.
Yes, it's
You can if you want. You don't have to go that far. I'm just kind of conceptually showing you how it necessarily won't be equal, but you're exactly right. You could if you wanted to. You hear what he said? Okay. So the top, what would the top factor to?
X minus 1.
X minus 1, x plus 3. Right? Or what did I say? Did I?
Shouldn't it just be x plus 1, x minus 1? Because
Yeah, because you said
Oh,
x
my bad, my
minus
bad,
2
my
is
bad.
x
The top simplified to x squared minus 1, right?
plus
So a difference of squares. My mistake. Thank you. So it'll be x plus 1, x minus 1. Which would then cancel reduce. And what am I left with, guys? X plus 1, which my slope would end up becoming what? 2. So f prime at 1 would be 2. So coming from the left, it's 2. But coming from the right, it's 3. Are those equal? No, because they're meeting at a cusp. You with me? It almost feels like the corner, if you will. Like if you had a piecewise function that did this, there's a cusp. A slope of 0 is meeting a slope of 3. This is the same kind of feeling. It's a cusp because the slopes are different at x is equal to 1. Okay?
The x plus 2 or x squared plus 2 equation still has, I guess, a limit going towards 1, 3. It just has a different slope at that exact point.
Yep.
Okay.
You with me on that? Okay. Yes.
so the derivative does not exist.
So, well, you'll say this, that, yeah, you could say the derivative does not exist.
Because
The-
the left and right.
The left and right are different. You see how we're correlating this? And that's awesome that you guys can see it, because we haven't taken the continuity test yet, but you can still see it, and that's good. It should be strengthening your both one-sided limits with continuity. Okay? Alright.
so for that, if this was like a test question,
If this was a test question, you would say it's non-differentiable at 1, because the slopes are not the same.
okay, so we still have to work both sides.
Yeah.
even though
What is non-differentiable?
Means that you can't take the derivative because they're not the same. You know how whenever we had with continuity, we had like the limit if you approached, let's say 1 was 2, but I could say, what if f of 1 was 3? Then we would say it's not continuous, right? Because of the third rule of continuity. The third rule meaning the limit would not equal the y value. You with me? This is saying it would not be continuous if I have two different slopes. This is kind of what's going on. If the slope from the left is 2 and the slope of the right is 3, it's non-differentiable. Okay? Alright. Let's move on to this one. Let's break things down a little bit easier. Guys, where do you see things that are not continuous? What x values?
It's like 5.
At 6. What else? That's it, right? That's the only place where it's not continuous. Not differentiable means we can't take a slope.
8, 3.
So 8,
Maybe
3, 5, 6 for sure, right? Because it's not continuous. It has to be continuous first. And there's one more.
Oh, 4.
4.
Because it's for
Because it's a vertical tangent. So what we learned today was vertical tangents are non-differentiable, cusps are non-differentiable, and also it has to be continuous. Otherwise, it has no shot of being differentiable.
So at 4, is there actually a vertical line there?
There is a vertical tangent, and it almost feels like it's touching at 2 places rather than just 1. You with me? But local linearity is only focusing on that one little spot right where it actually touches. And it would only touch at 1 vertical tangent.
How do we know if it's vertical tangent?
Because it'll be a vertical line.
So it wouldn't be a function then?
It can still be a function, it's just not differentiable there. Let me show you real quick. If I had a graph that did this and it met another graph that did this, the slope here would be like a positive 3, positive 2. But if I had the same graph and it doesn't meet like this, it meets more so like this, then it's going to be a vertical tangent where it's straight up and down.
Wouldn't that be touching more than 1 point?
So, but again, you're looking at local linearity, you're looking at just that one piece where it would touch. Don't let it keep going forever, per se. For instance, let me show you real quick on other ones right here. It'll help out with this one. When is the slope 0? At B, look, I'm going to draw a small one, and E. I drew a small little piece, a local linearity piece. You with me? A small little snapshot of B, and it only touches 1 point. Now, when would the slope be positive? At C? Now here we go. A small little piece. Let's not keep going, because if we did keep going, we could see that it could cross at other places, right? We're just doing a small local linearity piece, and it's touching 1, and D could also touch like 1 right there. Are you with me? And then which ones would be negative? A and F. So A could be here. Again, small little piece. F, small little piece. Yes?
When you draw the pieces, does it matter which side it's on?
It does not. So, nice questions. Because look, if I drew a line with F on this side, you could see, ooh, it's going to touch maybe 2 spots. But again, we're only focusing on local linearity. Either way, both lines are parallel, and it's at 1 point that has 0 dimension, it will be the same steepness. Okay? Alright. So now let's go to this last one. I believe this is it. Yeah, this is the last one right here. And then I'm going to record some examples for you guys for IVT from the supplemental to help you out, okay? What form of derivatives that we learned today do you see right here? That's alternative form. F of x is listed first. It's not f of x plus h minus f of x. It's the other way around. F of x minus f of c. Alright, so we have a must be true, might be true, and a never be true. And I want you to volunteer, if you like, and tell me what you think the answer is, and then tell me your justification. Why do you think that? So A, who would like to volunteer for A? A is saying f prime at 5 is 3. Is it true? Is it must, might, or never? It is must. For bonus points, finish it off. What is your rationale? Why is it a must?
Because you plugged in 5 at C and then the answer became 3, which is means f prime 5 equals 3.
Okay, yep.
Let's just say the general limit exists.
Say again?
The general limit exists, so it's going to be differentiable at that point.
Okay, you see if I put both of theirs together, this limit does exist. And this limit, just like Omar said, equals 3. And if we know that this is the same as f prime at said 5, then I can say f prime of 5 must equal 3. So putting both of those together does in fact give me the answer and justification that I'm looking for. Y'all see it? Okay, let's do B. F prime at 5 equals 0.
I think it might be true, right? Because we don't know. In the other example, when it was a piecewise function, we had like f prime of that.
This is a good mistake to make. This is a good mistake to make. Listen. Because, no, it's a good one because this one right here goes with what Omar was talking about from before. Remember how he said positive or negative if I'm approaching for the left or the right? This one says the general limit. This one is saying from the left and from the right, my slope will be 3. You with me? So is there a cusp? No, there's not a cusp. But I liked where you were going with it. It is a good mistake to make. I'm still giving the team points because it is a good mistake to make. I want you to understand those misconceptions. Okay? So anyone, what's the answer to this? Never. We already know what the slope at 5 is. The slope at 5 is what? 3. Okay? How about f of 5 is equal to 3? It might be true. We don't know. We don't know what the graph looks like. You know what I mean? So at 3, 1, 2, 3, 1, 2, 3, 4, 5, it could be a point. And whatever the graph is, we know that the slope is 3. So a slope of 3, the graph could look something like this. You with me? But the thing is, does it have to be a y value? Oh, right now, what am I showing? I have it backwards, don't I?
Yeah,
that's why the looks were looking. So I needed to draw this more so of 4, 5, 1, 2, 3. So right here, it could have been there with the slope of 3. It could have, if the graph looked like this. But the graph doesn't have to exist there. The graph could have been way up here, still with the slope of 3. You with me? So this is definitely a what?
A might.
Might. F is continuous at x is equal to 0. Maybe. We don't know. It's a might. We're not even looking at 0. 0 is over here. AKA, there it is right there. We don't know if it's continuous, but we don't care. That's not our local linearity window that we're trying to snapshot. We're trying to see at x is equal to 5. Right here, or here, whatever it is. F of x is continuous at x is equal to 5.
Might.
Must.
I heard all 3. I heard never, I heard might, and I heard must. Guys, it has to be a definite must, because if you're not continuous, if you're not defined as a point, you have no shot of even being differentiable. Okay? So it must be continuous at 5. For a lot of extra bonus points. And because we had all 3 answers, I want to ask this question. Who can tell me, by the top of their head, a function that is continuous, but is non-differentiable at a specific point? Think of parent functions.
I think like absolute value with the
Absolute
V.
value with the v. The absolute value with the v is continuous. You just saw me draw that without lifting up my pencil. But is it differentiable everywhere? No. Okay. So because you're continuous, does it automatically mean that you will be differentiable? Yes or no? No. But if I am differentiable, does it automatically mean that I must be continuous? Yes. Do y'all see that? If you are differentiable by default, you better be continuous. You have to be. But the other way around, exactly with the example that Danielle just gave to us, you can be continuous, but it doesn't mean that you're differentiable.
Also, if it was an odd power function, does that mean it would have to have a vertical orientation at some point?
Odd powers don't necessarily have vertical tangents all the time. They can have, depending on there's other pieces to it, like a polynomial, that it could tilt it a little bit and change it. As far as it being like really, really steep, like slope is 2,000, as opposed to a vertical tangent.
So on the normal, like,
X cubed, yes, then that's different.
there would be the vertical
Okay,
tangent.
let's talk about x cubed just real quick because he brought it up. X cubed looks like this. Is there a vertical tangent at x is equal to 0?
Yes.
Oh, no.
Yes?
There's not.
No.
No, that's what.
So this would go from, look, this would go from steep, less steep, less steep, less steep, and then probably hit some kind of steepness there, and then go back to these.
So at 0 would not be a horizontal. Oh, because you can't hit it.
So, and you'll learn this when we go into derivatives. The function is x cubed. The derivative, aka f prime of x, is 3x squared. So if I put 0 in there, the slope at 0 would actually go to a horizontal tangent. So he was saying vertical tangent. This would be a horizontal tangent.
If it was shifted, then it could have a chance to be vertical, I guess.
I think what you were talking about was cube root of x.
Oh, yeah, that's the one.
Cube root of x would look like this.
Yeah, that's what
Okay?
I was thinking.
And this would go to a vertical tangent.
Okay, yeah, that's the one I thought.
Okay.
Vertical tangent.
Was there another question? I thought there was. Okay, no worries. Guys, the last one. Please, please make sure that you get this in right because you're going to be tested over it next Tuesday. Is this might, must, or never?
Must.
Must, right?
This is must. Because this is the third rule of what?
The
Continuity. So that must be true for the theorem to hold, for it to be continuous, for it to even have a shot of being, right, differentiable. Okay? Okay, so that's it on the video. Now I'm going to record some videos for IVT.